talk primarily, okay. So thank you for the opportunity. So I will cover something along the semantics in medicine and try to touch upon with expert data and application perspective. So I come from the healthcare side of the background. So for those who are in the healthcare, it's kind of knowing there are so much unstructured data. For the clinical side, for the other side, they may not know there's so much data in the clinical domain which are unstructured, which are also crucial to do anything related to health data. We generally call this as the data iceberg issue. Basically, when you receive a data set, those are just a surface level information. And there are many information actually hidden, which are not exposed. This is the context level information about such a data, such as a clinical guideline. Any clinical guideline change, any policy change will influence how you interpret the data. Go back to the first article we consider to be the Healthcare AI Theory Foundation, which is this article published in 1959. Many of us know it's not born by then. So this is called Reasoning Foundation for Medical Diagnosis. If you look at this statement, this is a follow the traditional data information knowledge wisdom paradigm. So the first thing is that they obtain the case facts. This is the data connection. Then the second is evaluate relative importance. So this is basically try to get information. And thirdly, try to make a differential diagnosis. This is leveraging the knowledge of the clinicians to handle that. And lastly is the action, which is how to, based on the information gathered, taking action. And those things, as you can see, is a complex reasoning facts. And when you translate to patient records, this is the unstructured clinical notes. We're not, they generally follow the format as showing here. They have a header, body, section, but all those actually have meaning. So where it's located, a token or natural language, where they located, it impact what it means. So in order to create understand that, we actually need to go through this triangle. First, whatever present there, they have a context about this document, which most of the time not accessible for data processing, which is called context omission in clinical domain, is that those contexts are not digitally represented for that data to be interpreted correctly. Then secondly, you have beliefs. This is come to the clinician subjective assessment and also patient's assessment report their own. So those are the beliefs. And lastly, is intentions is that how this document end to be also relate to what patients wants this to be. And there are so many factors related to clinical documents, which is not simply just a text data. There are so many things behind it, which to correctly interpret it, you actually need to have those information to be inferred and understand. So the language, the soul of medicine, many of you probably experiencing this. We can read literature, we can do something, but when it comes to clinical notes, clinical language, there are so many terms we probably not see them in the general English domain. So we consider medicine itself has their spatial linguistic structure. So 75% of all medical terms are derived from Latin or Greek. And the one thing in the clinical domain is that the time is very pressure there. So they generally try to convey the greatest amount of information with the least confusion and the most precision. And that's the reason you can see a single medical term can describe a disease, a condition, or procedure that might take several words. And you also probably see abbreviations, acronyms and shorthands, all those structure tend to appear more frequently in the clinical language. So how do we learn the medical language? We know in natural language, we learn through, many different ways. Kids learn languages through observe, through learning, through reinforce feedback. When it comes to medical language, this is also similarly people learn from leveraging the expert resources and how the language performed. Secondly, how those case reports or those different documents, how the language was shown there. And lastly is that when they're actually creating a clinical notes, they learn from that to be able to document that medical language. So we all know that right today, natural large language model becomes pretty popular. And why it's become so popular, it's a statement. We think natural language is a surrogate of human intelligence. I distinguish natural language from AI-generated language because those are not considered natural language because they're not reflecting what a human generated those language. So to understand the medical language, I don't know how many of you know this. This person name is Zilak Harris. We consider him as a founding father of language models. And if you don't know him, probably Google him. I know his student is very popular. Noam Chomsky is very popular. So he is the advisor for Chomsky. So he indicating, to understand medical language, there are certain things we need to figure out. One is dependency relation. So there are clinical terms. Some are what we call level 0 clinical terms. There are some terms that does not have meaning and they count on the dependency to have meaning, have action on it. Second is paraphrasic reduction. This is make the clinical language more challenging and more interesting to tackle. Basically, many sentences, simple sentences, tend to be merged together into a compact semantic equivalent forms. Those is translated to you have the same meaning, but have different way of representing in the natural language. Third is inequality of likelihood. Basically, when you observe something, there's a tendency, the dependency relationship has some difference in the likelihood of appearance. Those are distributional semantics, all those things we consider about. Lastly is the sublanguage constraints. So this basically means that some linguistic structures or language structures are specific to a domain. And this a good example is the blood pressure. They put as those two parentheses, those are the sublanguage constraints. If you try to understand the language without knowing the sublanguage constraints, you probably couldn't get the meaning out of it. And understanding clinical language is not anything new. And back in 1965, there is a project called Linguistic Stream Projects, where Professor Sager from New York engaged in natural language processing research. So the results is more take the traditional AI approach, which is the expert-based system, try to create rules, resources for language terms, and constraint grammars, and all those related pieces. And that project, if you go to the website or go to the this article, you will notice is that they transform uh, um, a clinical data into a natural language representation, and vice versa. You can generate a computational representation based on the natural language. Um, so my thesis research 20, 30 years ago is about how do we use machine learning, use knowledge base to resolve the meaning of those biomedical terms with ambiguity. So we call this as word sensitivity ambiguation problem. Word sensitivity ambiguation problem is the sometimes we call AI hard problem. They are very challenging to resolve. And and even with the large language model, current technology, we still consider this is not a solved problem. Basically, in order to understand it, you do need to have a sense inventory, but that sense inventory can change depending on the context. So we don't know what's the set of meaning of a token or phrase is. So this is basically the we leverage in this thesis research. We leverage the semantic context to predict the meaning, and where the use distance supervision approach to use knowledge base to derive semantic annotated corpus, and from that to do supervised machine learning. And fast forward in 2020, we additionally look at the standardization, and just have one of my PhD students continue this line of research, try to transform natural medical language into a standard representation using standards. Here is the HL7 FHIR standards. So basically, any free text that you can codify as the standard data models in HL7 FHIR. But this is prior to LM era, and we use the traditional machine natural language processing pipeline, use deep learning related architecture for classification. On the top is you see the natural language. On the middle is the concepts, extraction. On the last is the codify those type of things, HL7. But right now, if you use some large language model, you ask them to transform those into a structure, they can do pretty well, except the code, the concept code itself may not be accurate, but the structure using LLMs are pretty good right now. One thing I want to call out is that we do notice the difference between expert semantics versus data semantics. So expert semantics is reflecting to the knowledge captured by domain experts. And so SNOMED CT here is reflecting the expert semantics. So we use this knowledge base to derive a connection of annotated data. Then we blindly, evaluate that against the manual curated data from clinical text. So what we do using the distance supervision, using the knowledge base like SNOMED CT, we have pretty good performance. However, when you come to true natural language, a natural generated medical text, the performance for some of the relationship dramatically decrease due to the difference between what we capture in knowledge base and what the actual clinical text complexity associated with it. So if you do any kind of clinical natural language processing tasks, if you are generate your distance supervise your clinical training data, you need to pay attention to a blind evaluation. If without it, it's may not be reflecting that. So what's this? Sorry. So I want to capture something. Even I did so much work in the clinical statistical natural language processing side, but I do notice one challenge you're facing is that we tend to struggle to forgive AI mistakes, basically those that come from data-driven approach. And this is give you another example here. Back in 2013-ish, we've been tasked to do clinical decision support for cervical cancer screening. And I show an expert-based AI system here for clinical decision support, where the data for this clinical decision support are coming from a natural language. So this is a very complex tree. And this was have 41 decision points and 13 for routine screening. It's very challenging to maintain, but the clinical users, physicians actually use it. And we were wondering why they're using such a complex system, and against the simple system like decision tree models we come up. And the behind reason is that this is a more consensus driven. They can see and understand the decision logic, so which make them accept the use of it. When we have machine learning based model for them, they don't know why it's come to the decision. So it makes us thinking is that in order to get users to use those systems or use the AI, we do need to factor in the domain and the user part, their input into the conversation. Even this is such a complex system, it's difficult to maintain. They still like it, they still deploy it. Even we have a simple model, but they are having challenge to deploy it because they don't trust, don't understand. And this is those are like 10 years ago, decades, 30 years ago. Right now, I think we probably face something different, maybe to the opposite way. People started to use generative AI, chat function or AI to handle many disease healthcare, health-related information, including healthcare systems, try to use the apps to help with the ease the shortage of primary care. So I want to, the remaining time, just to quickly go through is that we see some high risk associated with this trend. This is the preprint current under review for context matching is not reasoning. Because most of the headlines regarding the clinical AI for healthcare or for clinical question answering depends on the some of the standard evaluation, and so basically the medical license exam benchmarks, this is generally used to test the knowledge about the future doctors, and those was try to assess their clinical capability of those, and how can generative language models to handle those benchmarks. We already know from the news and social media, they do pretty well. We trust those questions to licensed doctors in the real world. So if generative AI has this capability to answer those questions, so we should trust that. But there are so much issues related to this type of problem. And I know there are huge incentives for using those exam questions because they are available. They you don't need to spend effort to do the evaluation, just use those existing questions. And they score very high, GPT-01, and we know they are all over 90s, 100 for those questions. So these numbers are a huge driver behind the hype surrounding generative language models in media and the industry. But is this valid for data-driven generative AI? Multiple choice question is the assessment of several key assumptions. First, we assume in general human errors notwithstanding is that the successful reasoning and understanding of this is that human leverages their inference capability, and the human memorization is limited. We all know that. So basically, those question answering related to medical exam is have that assumption is that we have limited memorization as a human. Therefore, the test of the knowledge of this will help handling the inference and the generalizability of those components. So for human, we do believe when we rephrase in the content of the question will not change the exam's answer as long as the semantic content remains the same. So syntactic variation has limited impact on human memorization and the knowledge application. So basically, the know the right answer implies that you will also be able to identify when no correct answers are presented. So this is the assumption of those medical exams. But so is this true when we test those generative language models? So we want to test whether those assumptions hold true. Basically, if we alter, did prompt permutation or any kind of things, does those models still answer them correctly? And if we change 4 or 5 options based on successful solves, and so there are so many things we did. So in order to answer those, so we leverage 4 data sets, and we leverage all this available during the experiment time, all those models currently being leveraged for the news industry advertisement things. And we do prompt permutation. We sample 100 questions from each data set where all those models did correct. And so since all those questions are answered, so most of the, if you do the whole training, set, those are all receive pretty good performance. Large model have good performance, and a small model all get good performance. Those are their baseline performance. So we did experiment first to try to see if they're doing data memorization and expand the context space. So the first experiment setting here is that so instead of put the correct answer as C here, 5 options, we do this into 2, to create a lot of options. Human will be able to find, and K will be, correct answer. And we do a lot of test the answer consistency by removing some context clue. This is a second experiment setting. And the third is rephrase the prompt in certain way to that. So there are very clear problems. Many of those, in the literature already reported, and we did the study last year. So but you can see, if we shuffle all those different settings, the response from those models dramatically different. And when we have the context to be removed, the answer also have bigger issues. So this is just showing you that another thing we observed is that small models tend to take in shortcuts, despite they can answer those correctly before, but they dramatically decrease to those. And we are actually wondering, because of the navigating space for small models, through the small model distillation and this, they lose the capability of navigating to the right answer when you change the prompt, when you change the question format settings. So huge issues there. And for scenarios where there's no correct answers there, the model, different model have different performance, but you can see they're inconsistent in that. So this is, trying to just show most of the reported measurements are more come from memorization, and the larger models tend to have more space to navigating to the correct answer. When small models, when you change the context, change the settings, they tend to have significant failure. So remove of context and need reasoning model be more inconsistent than best model. So we also test some reasoning models, so they tend to not have the reasoning capability. Limited context effect globally irreversible reasoning or parameter size. If we get context occlusion and depends on the model training strategies, not on the baseline performance. So basically all the tests we did here is just to try to show something is that a context matching capability by the generative language models are not reasoning. I know the AIML field do a lot of consider those on reasoning, but if you go back to the foundation of language, you will start to know those are foundationally not really have the knowledge of the language, but more about the patterns they have. So those are easy questions. All models are got correct. For the real world consistency will be worse. So what they have is memorization, not a comprehension, not really have the language knowledge. So of course we're not see those are not useful. They can do a lot of things with such a thing as that in order for us to use those language models, we need to evaluating, we needed to test their model reasoning and the semantic consistency in the real world setting. This is the last two slides. I want to call on responsible AI. So many, we see this continuous July 14th in this news. So it's basically many in US consider AI general health information useful and reliable. We needed to pay attention to the decay effect curve because you don't know what you don't know. And this is pieces is that we call Nienberg law, the bucket theory. The growth of our humankind and move forward as a human creativity, all those things depends on our ability to have that human intelligence. We're a little bit concerning giving this, the domain experts in the future maybe become the scarcest resource. We all converging to something which may be biased, which may not represent the positive trends forward. I think that's what I have. I can answer any question you may have.
Thank you. Great, Dr. Liu. So I know time-wise, we're over time. Just maybe have one question from the audience. Yeah, otherwise, it's recorded, so we can, this is her email here. You can ask her directly. So we will post the video on our website. Thank you very much, everyone.
Thank you. Sorry
Yeah.
for
Thank
being late.
you.
Okay, bye.
Bye.